In this lecture, we're going to talk about finding the equivalence point in an acid-base titration using indicators. Most often, titrations are done to determine the concentration of a solution. In this example, we have a strong base with a known concentration in the burette, and we'll add that to a known volume of acid in the flask. The indicator will signal the end of the titration with an easily observable color change. This allows us to calculate the molarity of the acid solution using the concentration and volume of strong base delivered. A pH electrode can register the changes in pH to a 2 decimal place accuracy, but can easily cost hundreds to thousands of dollars to purchase. A less expensive option is to select an indicator that shows color changes as the pH increases or decreases through the pKa of the indicator. Indicators themselves are either weakly acidic or weakly basic compounds. In this example, we see phenolphthalein goes from a colorless solution at low pH to a vibrant pink color at pH 10. This color change occurs as the molecule changes shape to accommodate the addition or neutralization of acidic protons in its structure. Because these color changes are so dramatic, it doesn't take but a couple of drops of the indicator to signal the equivalence point of a titration. Now notice the pH 9 test tube. We could say this color is intermediate between the acidic and basic forms of the compound. This gives us an idea of what the pKa value is because the color change takes place when the pH equals the pKa. It is important not to mix up the equivalent point of the titration with the end point of the indicator. The goal is to match the end point, or pKa of the indicator, as closely as we can to the expected pH of the titration's equivalence point. Here, the endpoint of phenolphthalein is found by titrating the indicator directly with a strong base. If we repeat this process for methyl red, we see that the color change actually occurs over the range of pKa plus or minus 1 pH unit. When this pH is equal to the pKa of 5.1, we see the intermediate orange color resulting from the mixture of the yellow basic form and the pink acidic form. When the concentration of the basic form is 10 times greater than the acidic form, we see only the basic form of the indicator, or a more pure yellow. When the concentration of the acidic form is 10 times greater than the basic form, we see only the acidic form of the indicator, or a more pure pink color. An indicator error occurs when we do not match the endpoint of the indicator to the equivalence point of the titration closely enough. For example, if the pH at the equivalence point of the titration occurs at pH 5.5, bromocresol green wouldn't be the best indicator choice since it changes from blue to yellow at pH 4.5. Though it's not perfect, bromocresol purple would be a better choice of indicator as it changes from purple to yellow at pH 6. In this example, we see the titration of a strong acid, the orange curve, compared to the titration of a weak acid in purple. The appropriate indicator for the strong acid strong base titration is clearly litmus paper, but not methyl orange, which would signal the change too early, or phenolphthalein, which would signal the end of the titration almost 2 pH units too late. What would be the appropriate indicator for a weak acid titration? Since the product of a weak acid neutralization is a weak conjugate base, phenolphthalein would be the best indicator. What type of pH-active compound would be best suited to a methyl orange indicator? A weak base would work best with methyl orange because the product of a weak base neutralization is a weak conjugate acid. As a final thought, it's important to note that the equivalence points of acid titrations become harder to pinpoint as the acids become weaker. This effect is even more pronounced in polyprotic acids given that their successive pK values become weaker as you remove more protons. Let's test what you've learned. If bromocresol green changes color from yellow to blue over a pH range of 3.8 to 5.6, what is the pKa of bromocresol green? The pKa will occur at the midpoint of the color change, which is at pH 4.7. Which color do you expect to see at pH 3.0? This pH is below the pKa for the indicator, so we'll see the acidic yellow form. Which color do you expect to see at pH 4.7? This pH coincides with the pKa of the indicator, so we'll see a mixture of the acidic yellow and basic blue forms, giving the intermediate color green. Which color do you expect to see at pH 8.0? This pH is above the pKa for the indicator, so we'll see the basic blue form.